So a little bit about slightly more advanced applications of multiple regression. We'll take a look now in more detail at sequential or hierarchical regression, and then we'll explore how can we code nominal variables and how can we test for variable interactions in regression models. As we discussed before, sequential regression is the situation when we add our predictors in portions, or even one by one. What happens when we do it? Let's take a look at this picture. So you remember that our dependent variable, its variance is a big pi. So when we conduct standard multiple regression, we include a bunch of predictors together. They are trying to bite this pie at the same moment. So each predictor gets only that slice of a pie that no one else gets. And then in standard multiple regression, your first predictor will get this part, your second predictor will get this part, and your third predictor will get this part. However, what happens if you start introducing these predictors sequentially? In the first regression model, you will only introduce predictor 1, IV1, and it will bite the pie without any other predictors present. That's why it will bite the portion of variance that is essentially the same as correlation, basically all the variance that it shares with the dependent variable. However, at the second step, you are going to add a second predictor, IV2. And then IV2 will only be able to bite this slice that IV1 has not yet beaten. Oh, sorry, I'm pointing at the wrong picture. Yeah, so this part that is not beaten by IV1. And then you add the third predictor, which will bite this part that was not beaten by IV1 and IV2. So in sequential or hierarchical regression, essentially we will have three different regression models. A model with just the first predictor, a model with the first and the second predictor, and a model with all three predictors together. And this model with all three predictors together, it will be exactly the same as standard multiple regression. But in the first model, IV1 will have this. In the second model, IV1 will have already this, and IV2 will have this, and so on. So to understand how it works in practice, let's take a look at an empirical example. But before we do it, when do we even want to use this hierarchical or sequential regression? Essentially, we want to do it when we want to see if by adding more predictors, we increase the R-square. And sometimes we want to do it when we want to test for incremental validity of some new measure. Imagine that you've developed a nice new questionnaire, and then nasty reviewers come to you and say, but it's already in the Big Five. And the Big Five model of personality traits, of course, it captures a lot of personality content. So you want to prove that your questionnaire captures something different. And you are trying to predict some important outcome. You give people to complete the Big Five and your questionnaire, and then you conduct regression analysis, and you show that after including the Big Five, if you include additionally your questionnaire, the prediction quality grows, the R-squared increases. And then it means that your new questionnaire has some incremental validity after the Big Five. Sometimes we want to test whether psychological variables explain any variance in addition to demographics. And sometimes we just want to compare different groups of predictors and see how the proportion of variance overlaps. To explore these advanced topics, let's take a look at another empirical example, which comes from a data set that I was recently struggling with. It is a survey of doctoral students conducted by my French colleagues, Pascal Hague, where almost 2,000 doctoral students from France completed a bunch of questionnaires. And the main goal of this study was to find out why do they suffer, what makes them suffer. So the dependent variable was their health, the number of somatic symptoms, a questionnaire called symptom checklist, so that the higher score means the larger number of symptoms, the larger number of health problems. And we used a whole bunch of different predictors, demographic variables such as age and gender, the year of enrollment in graduate school, are they first year, second year, etc. Discipline, and we had students from different fields, from physics to psychology. Satisfaction with supervisor. And this was a single question where the students were allowed to avoid answering. So there was an option, would not like to answer, and 3 different answer options, like not satisfied, average, and satisfied, something like this. We also asked them if they did any sports, if they slept well, and we measured perceived stress with a perceived stress scale, a questionnaire, which uses interval scale. So as you can see, there is a whole mixture of different variables measured using different scales, and this mixture is not so easy to deal with. But this is a data set where we had many different variables of different types, and that's why we wanted to do a sequential regression. How do you do sequential regression in SPSS? Well, it's very easy. Basically, you enter first the variables that you want to include into your model at the first step, maybe several of them, and then you press Next button, and you will have block 2 of 2, and you can include the variables for the second step. And also you want to compare whether addition of variables at each step increases your prediction. That's why you need to go to statistics and tap this little checkbox R² change. I have no idea why it's not tapped by default, but that's one of the troubles with SPSS. And that's how you proceed. So how do the results of sequential regression look? Essentially, it's pretty much the same as your normal regression. Only this model summary table now contains several models, and the coefficients are also given for several models. So in this simple example, I just used 2 variables. The first variable is age, and the second variable is year of enrollment in doctoral school. And here we compare those 2 models. So the first model, and SPSS here explains to us that here we only had one predictor, age. And as we can see, this model has a very small R², like 0.5% of variance, but thanks to our large sample size, it is statistically significant. So the significance is 0.002. And we can say that, yeah, age predicts somatic problems in doctoral students, and the beta coefficient is 0.07, but here maybe it's better even to use B coefficient, because age is measured in years, and it's easier to interpret in years than in standard deviations. So we can say that every year of age is associated with a 0.13 increase on the scale of somatic symptoms. Or one standard deviation increase in age is associated with a 0.07 increase in standard deviations of somatic symptoms. And this is statistically significant. So this is the model at the first step, model 1. What happens at the second step? At the second step, we use 2 predictors, age and the year of thesis. Obviously, these variables are correlated, because every additional year in graduate school makes you 1 year older. That's a bit of a problem. So what happens when we add the year of thesis? First of all, we look at this significance of R² increase, and we see that R² change is 0.011, which means that the year of thesis has explained 1% of variance in addition to age, And this increase is statistically significant. It's very good significance. But what happens if we look at coefficients now? So now the age, its effect is not significant at all. Age is not a significant predictor when we include this year of thesis in graduate school. And we see that every year in graduate school, the number of somatic symptoms increases by 0.43 points on the questionnaire, or by 0.12, one standard deviation of year of enrollment in graduate school increases somatic symptoms by 0.12 standard deviations. So these coefficients basically reflect the independent contribution of each predictor. So here we see the effect of age regardless of the year of thesis. So, and we see that age has no association with somatic symptoms if we control for the year of thesis. However, the year of thesis has a positive contribution, a positive association with somatic symptoms if we control for age. So what does it mean, control for? Basically, as if all the doctoral students entered graduate school at the same age. And this is this effect of year of thesis independent of age. So everything else held equal. All the other predictors in the model held equal. So in the beginning, in the first model, age was biting the pie and it was alone. But when we have age and year of thesis biting the same pie, we see that only year of thesis gets a large slice and age is left with almost 0, because it's probably less important. So doctoral students suffer not because they are older, but because their defense is approaching. And of course, this situation is very complex. There are many factors that predict health in doctoral students. That's why we want to explore all of these predictors. But we also have a problem. Some of our variables are nominal, like discipline, for example. What do? How can we include nominal variables into our model? And actually, it's very simple. If you want to include a nominal variable into your model, you need to recode it to a set of so-called dummy variables. And you need to create dummy variables by coding every level of your nominal variable. Imagine that your nominal variable has 3 levels: red, green, and blue. So red is coded with 1, green is coded with 2, and blue is coded with 3. So you need to create first the dummy for red, so that every person who likes red will get a 1, every person who likes green or blue will get a 0. Then you create in the same way a dummy for green. Everyone who likes green will get a 1, everyone who likes red or blue will get a 0. But what about a dummy for blue? The problem is that you cannot include the same number of dummies as the number of levels in your nominal variable, because then the system of equations will not be possible to solve. So you need to exclude one dummy variable. And which one do you exclude? You exclude the dummy variable for the group that you call a reference group. And this reference group will be used to compare all the other groups with it. And this reference group will be coded with zeros on all the dummy variables that you are going to include. So this is the type of coding that is most commonly used in social sciences. There is also another type of coding that is called effect coding. Essentially, it is the same. The only difference is that your reference group is coded -1 instead of 0. However, effect coding has some disadvantages. It is good for experimental designs when you have balanced groups, equal number of observations in each subgroup. Then you can use this effect coding, and it makes your interpretation easier because every coefficient will reflect difference from the grand mean. However, when your sample is not balanced, when the number of individuals for each level of your nominal variable is not the same, effect coding will result in artifacts. It will not. It will be biased. With dummy variables, there is no problem. That's why normally we use this dummy coding. And when we use dummy codes, the intercept in our regression will be the mean of our reference group, the one we have omitted from the set of variables, and the regression coefficient for each dummy will reflect the difference between this group and the reference group, either in raw score points if it's B coefficients, or in standard deviation units if it's beta coefficients. It might look a little bit abstract, but let's see how we can do it in practice, and it will be much easier. So in this data set, we had 2,000 doctoral students coming from different disciplines. And they just typed their discipline in a text box. And my colleagues used some kind of content analysis to classify those disciplines into larger groups. So we had a bunch of people doing humanities, arts lettres, some people studying history, some people studying social sciences, law, health, natural sciences, and psychology and education. As you can see, these groups are very diverse in terms of sizes. Some are large and some are very small, like law. What happens if we try to just conduct analysis of variance and see if these differences in discipline explain anything in our symptoms? So I conducted a simple one-way ANOVA, and all these differences in discipline, they explain about 1.9, almost 2% of variance of symptoms. So there are differences in how much doctoral students in different disciplines suffer. And here we see a graph. So the healthiest ones are from natural sciences, and the most sick ones come from humanities. But of course, we are not so much interested in this because we want to see if discipline has any effect after controlling for gender, for age, and so on. Maybe in humanities people take forever to write their thesis, and that's why they experience too much stress and they suffer. That's why in order to test this hypothesis, we wanted a regression model. And we wanted to code these variables into dummies. In SPSS, it is very easy to create dummy variables. You click on Transform Compute, and you enter a formula. The name of your dummy variable equals, and then in brackets, you enter your nominal variable equals value. So the disciplines in our case were coded from 101 to 107. So for humanities, I enter this formula dummy1 equals discipline equals 101. So as a result, this dummy1 will have ones for every individual whose discipline equals this, and it will have zeros for all the other individuals in the sample. And this way I have created dummies for all these groups. However, one of the groups needs to be chosen as a reference group. Which group to choose? Well, sometimes you have a substantive reason, but sometimes when you don't have a substantive reason, here I just chose the group that had the lowest score, and it was also the largest. So these were two reasons. Normally you want to compare with a large group, and normally you want to compare with a group that is on one end of this continuum. But sometimes you might want to choose one in the middle. Basically, it's up to you. So we chose sciences. what happens when we include all these dummy variables into our regression? So here you can see dummy variables for all the disciplines except for 106, because 106 is the reference group. We did not include it. And here we see this list of predictors, and the R squared 0.019, it is exactly equal to our eta squared from ANOVA, because essentially regression and ANOVA are pretty much the same. What happens if you forget to exclude one dummy variable? Well, SPSS will just throw out one of them based on its own reasons. And here for each discipline, now, if you remember that reference group is natural sciences, like physics or chemistry, for each group, we have this beta coefficient, which shows by how many scale points does each discipline differ from natural sciences. So for example, students in humanities, they have about 2.5 score points more on symptom checklist. And students in history 1.46 and so on. Or if you're interested in standard deviations, students in humanities are 0.16 standard deviations higher than those in physics are, etc. So this beta will basically be equal to Cohen's d if you calculated it for the difference between natural sciences and each of these groups. And as you can see, some of them are statistically significant, some are not. So this law group, it was very small, and this psychology group, it was also fairly small. But maybe it suggests that psychologists are not suffering more than people in natural sciences. So it's good news for us studying psychology. And now, of course, we can build our overall model, and we can include discipline into the model, and we can also include stress into the model. So here, for example, at the first step, I included just age and gender, and they explained about 6% of variance, pretty much. Mainly gender contributed. And then the year of thesis, which contributed additionally, and this was a significant contribution. But after controlling for age, gender, and year of thesis, the contribution of discipline becomes fairly small. Now, it used to be when discipline was biting the pie alone, it explained almost 2% of variance. Now it explains 0.7%, much smaller. But still, this is statistically significant. So we can say that discipline is a useful predictor. And finally, we included perceived stress scale. And of course, a psychological predictor explains a much larger proportion of variance, and it's very strongly significant. So the fact that discipline explains additional variance after age and gender and year of thesis suggests that people in some disciplines, maybe in humanities, they suffer more, but not because they are female or because they are older or because they take longer to complete their thesis. Maybe there are other reasons why they suffer connected to each specific discipline. So when we look at those results in detail, you can see also these beta coefficients, and you see that when we add gender, age, and the year of thesis, these beta coefficients have become smaller. So for humanities now, instead of 0.16, it's 0.10 standard deviations, but still it's statistically significant, fairly strong. But some that are weaker disappeared, and this is also okay. But perceived stress has the strongest effect. And when perceived stress is included, many of those previous variables become insignificant, suggesting that maybe perceived stress is a mediator. So we have explored how can we code nominal variables in regression. I hope that you have now some idea of how you can create dummy variables. Another important task that sometimes we are interested in is investigating interactions between different variables. For example, perceived stress. Perceived stress is an important predictor of somatic symptoms, but is it equally important for students in different disciplines or for males and females? Basically, the question is the association between stress and symptoms the same in different subgroups of our big sample of doctoral students? And in order to do this, we need to test for an interaction effect. This hypothesis is also called moderation. What is moderation? It's a situation when you have an interaction effect between two different predictors. For example, the effect of one predictor on your dependent variable might be different depending on the values of another predictor. For example, the association of stress with somatic problems might be different for males and for females. And the same question can be formulated. Does the interaction term, which is basically a product, you multiply predictor 1 by predictor 2, does this interaction term explain additional variance after controlling for both of these predictors taken independently? And basically, this is the same as interaction effect in two-way ANOVA. However, you can only apply ANOVA to nominal variables, and regression you can apply to different types of variables. That's why it's much more flexible. How can you plot an interaction on a graph? There are two different ways. So one way is to draw what is called a statistical diagram, where you have your predictor x, you have your dependent variable y, and a variable that changes the association between x and y. But by saying so, we make a causal assumption. Maybe it's better to say that the association between x and y depends on the values of this w. So this w is a moderator. However, this diagram does not always make a lot of sense, because sometimes these variables x and w, they are just symmetrical. They are two independent predictors. So you cannot say that one of them is moderator and another one is a predictor. They are both predictors and they interact. That's why this type of diagram, which is called path diagram, makes a bit more sense. And it's also easier to read. So here we have a product, x multiplied by w, which explains additional variance of our dependent variable y. And we call it an interaction effect. How do we do it technically? In fact, it's very easy. You just need 3 steps. First, you center your predictor. What does it mean to center? Basically, you subtract its mean from the predictor. If you don't want to bother, you can just standardize it to a z-score. It's not really important. In principle, you can even skip centering or standardizing. However, the coefficients will be easier to interpret if your predictors are centered. If they are not, it will be slightly more tricky and it will require a plot to understand what's going on. The second step, you create interaction term. Basically, you take 2 predictors that you have centered or standardized and you multiply them. And the third step, you conduct a sequential or hierarchical regression, and you enter first both predictors, and then you enter their interaction term. And if this interaction term explains some additional variance, it means that the interaction effect is there. The only important thing is that it normally makes no sense to standardize dummy variables. So if one of your predictors is binary or a dummy, there is no reason to standardize it, because by standardizing you set equal scale, but a standard deviation for a binary variable like gender, for example, makes no sense. So if you have a binary variable or dummy, normally in regression we just keep them as they are and we multiply. 1/2 of your sample will get values of 0 if it's a dummy with 0, 1, but don't be scared, this is intended. So let's do this in our data set. We have a variable gender, in French sex. We code 0 males and 1 we code females. And we find mean score for perceived stress in all of our large sample. It's 41 point something. And when we center, we just subtract this mean from each individual score. So we compute new variable, this perceived stress minus this mean, which we got from descriptive stats. And then we create an interaction term. We'll multiply this centered perceived stress by this sex variable. So for all males, this interaction term will be 0. And for all females, this interaction term will equal to something that is the difference from average perceived stress. This is okay. This is intended. So what happens when we include these guys into our regression model? Let's just look at a very simple model. At the first step, I've only included both predictors, perceived stress and sex, gender. And here we see that perceived stress obviously explains a fairly large proportion of variance. The beta coefficient is 0.45. And for gender, it's 0.17. Both are statistically significant. But what happens when, at the second step, we include their interaction effect? Here, as you can see, this interaction effect is statistically significant. It is fairly small. It only explains 0.3% of variance. But actually, this is normal because interaction effects are always very weak. That's the reason why you can only detect them in very large samples. And meta-analytic studies show that an average size for an interaction effect is something like 0.002% of variance. So not strong at all. And here, now when we have 3 variables, this interaction explains its effect is statistically significant. Significance is the same because just one predictor was added. And 0.10 for the beta coefficient. And because we have centered our perceived stress and because we have a binary variable for gender, it's fairly easy to interpret. If it's 0.10, it means that higher score on one variable combined with higher score on the other is associated with higher score on the dependent variable. So if a person is female and she has a higher perceived stress, as a result, she's more likely to suffer from somatic symptoms. However, it's not always easy to interpret interaction, especially if those predictors have different signs. That's why in order to interpret an interaction effect, the best strategy is just to plot it. So in SPSS, we can very easily plot it by going to graphs legacy scatter plot. And here on the vertical axis, we plot our dependent variable. On the horizontal axis, we plot one of our predictors. And the second predictor, if it's nominal, it's very easy. You just say set markers by, and your sample will be split into subgroups. If the second predictor is interval, you will probably have to recode it. For example, in 3 groups, like lowest third, medium group, and high group. This is just to be able to plot it. Or sometimes you create a low group, which is 1 standard deviation or lower, middle group, and high group, that is 1 standard deviation above the mean or higher. There are different strategies. Or just below the mean, above the mean. So it depends what you want. And then you get the resulting plot in the output, and you're supposed to double click it and click on this very little, very nasty icon, because it's always very hard to find it. Add fit line at subgroups. And once you click on it, tada, you will get a plot that looks like this. where males and females will be shown in different colors. SPSS has chosen blue color for males and green color for females. The R squared for males is 0.17. So the correlation between stress and symptoms for male is square root of this 0.17, something like 0.40. And for females, the R squared is 0.23. So their correlation between stress and symptom in females is closer to 0.50. So the correlation in females is stronger. And basically, interaction effect tests this hypothesis. Is there a significant difference in the strength of this association into groups? And because this interaction effect was significant, it means that this difference in the slopes for males and for females is statistically significant. And we can say that when people feel higher stress, if they are female, they are likely to report a little bit more somatic symptoms than if they are male. And we can check different interaction effects, and then the ones that we are theoretically expecting or the ones that we are particularly interested in, we can include into the model. So I hope that you've got the general idea of this approach. This is basically the final model. Here, for simplicity, I've only listed variables that were included into the model at each step, and I tried to predict perceived stress and somatic symptoms, symptom checklists. So first, we see that females and older students are more likely to report more stress and more symptoms. Then the year of thesis is an important predictor. The discipline is an important predictor. But also satisfaction with supervision, we can also include it if we code it with dummy variables. So satisfied is reference group, medium or not satisfied are dummies, and those who are not satisfied with their supervisor report higher perceived stress, and it's a very strong effect, 0.20 standard deviations higher perceived stress compared to those who are satisfied with their supervisor, and 0.13 standard deviation higher somatic symptoms. Then for sports, again, it's an ordinal scale, so it's best to code it in dummies, and no sport we used as a reference group. So those who do at least some sports, they report less stress and fewer somatic symptoms. And sleep quality, because the distribution on that scale was close to normal and there were 5 response options, I just treated it as a single predictor. And we see that sleep quality is inversely associated with perceived stress and somatic symptoms. So those who sleep better, they experience less stress and fewer symptoms. But there were also some interesting interactions. Stress is more strongly associated with symptoms in females after including all those variables. So this interaction effect is still significant. It's more weakly associated with somatic symptoms in those who sleep well and in those who study psychology, in contrast to students of all other disciplines, which is really good news for if you are going to go into graduate school. Of course, the question is, how do you interpret these findings? You can make a causal conclusion like French scientists have discovered that by sleeping well and studying psychology, you get a better chance to survive in graduate school. However, this interpretation would not be warranted because this study was a cross-sectional study. We basically measured a bunch of things at the same time. And the causal links between those variables might be completely different. For example, is it lack of sleep that leads to health problems? Or maybe it's perceived stress that leads to both health problems and sleep problems. Or maybe somatic problems arise for some other reasons. So unfortunately, there is no way to be confident of that. The only way to be confident is basically to improve the research design. So ideally, I would conduct this kind of study every year, and I would monitor doctoral students to see what happens to them. But I hope that you have gotten an idea of how can we deal with hierarchical regression, what do we use it for, and how can we use it to test for interaction effects. In fact, if you want to test for some nonlinear effects, you use exactly the same approach. For example, if you want to predict something not with a linear function but with a quadratic function, you do the same thing. You center your predictor, then you square it, and then you enter squared predictor after entering your predictor as it was at the first step. And this will be polynomial regression. And you can easily add binary predictors without any recoding, just code them as 0, 1. And you can add nominal predictors by converting them into bunches of dummy variables. Of course, if you want an interaction with a very complex variable, like for example, discipline, we have 6 dummy variables for discipline. So if you're interested in interaction between perceived stress and discipline, you would need to compute 6 interaction terms and enter them all at the same time into your model. So with many levels, it becomes very cumbersome. That's why it's better to use interval variables. But of course, sometimes we have no choice. And the principles for building the model are still pretty much the same. Try to use a minimum set of predictors that should be comprehensive and that should be based on theory. So we have explored a little bit simple regression, hierarchical regression, and moderation. Let's take a very quick look at mediation. What is mediation and how can we estimate conditional indirect effects?